Well, thanks a lot, Chris, for inviting me to give this talk. So today I'll be talking about a project that I've been working on over the last 2 years, quite a bit. And the talk is about developing deep learning models to automatically extract millimeter scale deformation in InSAR time series. So it's work that has been in collaboration with Romain Jolivet, Manon Dalaison, Paul Johnson, and Claudia Hulbert. The main two InSAR experts I've been working with for this project are Romain Jolivet and Manon Dalaison. Romain Jolivet is an assistant professor at INS in Paris, and Manon Dalaison is a PhD student in his group. So first, I'll give a small introduction, some background about deep learning and CNNs. It's going to be shallow, ironically, but could be useful if you're not too familiar with deep learning, because I'll talk a lot about deep learning for the rest of the talk. And CNNs in particular, I'll be talking about. So a type of deep learning model, convolutional neural networks. So they have an interesting history. So I'll also briefly mention that. So they were actually introduced in the 80s by Japanese researchers, Fukushima and Yamaguchi, during the so-called AI winter that took place in Europe and the US. So during the 80s, after, so basically AI research took a certain path in Europe and in the US, the path of expert systems. So basically trying to develop AIs with explicit rules. And it didn't pan out as people were expecting it. And what follows was the so-called AI winter. So there was no funding, no research for AI in the 80s in Europe and the US. But Japan carried on, basically. And that's when CNNs were introduced. Can you listen? Can you hear me? Because the screens are frozen.
Yes, I can hear you.
Okay, great.
Yeah, we can hear you.
Great. So Japan carried on, and that's when CNNs were developed by those two researchers. And the way we're using CNNs nowadays, that's going to be my take on it. But I think there were two turning points that made modern deep learning possible. CNNs, the use of CNNs possible in all kinds of applications, including in earth science. So those two turning points were the development of backpropagation for CNNs in the late 80s by Yann Lequin, which makes it possible to efficiently train CNNs. So the first CNNs introduced by Fukushima and Yamaguchi were very hard to train. And Yann Lequin developed a mathematical trick to basically differentiate CNNs. So it's easy to train them, to adjust the weights to optimize their performance. So that was the first turning point that made it possible to train them. And the second turning point that made it possible to really very rapidly train them on large data sets, which made it possible to train them from scratch. So before this second turning point, so actually CNNs weren't trained from scratch. Small portions of the CNNs were trained independently, because it was just too slow, too costly to train them all at once. So all those parameters I'll talk about in the next few slides. So the second turning point that made it possible to train them from scratch is the GPU implementation. So implementation on gaming chips, which gave around 2 orders of magnitude speedups in general. And so that was in the 2000s. And that took place more or less in the same years as the development of ImageNet, a large data set of labeled images, natural images, so cats, dogs, cars, etc. Millions of them labeled by hand, so it was an enormous amount of work to develop this database. And the combination of those made it possible to train deep learning models, CNNs, from scratch on GPUs. And from that point on, basically, CNNs trained on GPUs and large data sets from scratch have been outperforming any other computer vision technique, and even the human eye. So that's basically my take on what made it possible, the training of modern CNNs. So now I'll talk just a little bit on how they work. Just give some elements to some intuition on how they work if you're not familiar with them. So at the heart of CNNs are convolutional layers. So, and the idea behind those convolutional layers, so they're stacked in a deep in a CNN, in a deep CNN. I'll show the architecture in the next few slides. And so the basic operation that's repeatedly done throughout CNNs is this convolutional layer, and it's actually a cross correlation. What it's doing. So this cross correlation uses a kernel. For deep learning, the kernels are going to be learned from data, but you might want to set it yourself, for example, in some particular applications. So it doesn't really matter at that point. What matters is that it's simply parsing a kernel throughout the data. And so this kernel that you see here, so it's here you see an animation taken from a tutorial made by people at Stanford. And so each time the kernel scans a new part of the image, the overlapping values are multiplied, and the sum of those gives the corresponding value in the feature map on the right. And so this feature map will be what's used to extract information from the input. So the heart of the CNN is this simple procedure, and it's done many times throughout the network. So here I'll give you again a simple example of this kind of transformation, image transformation that CNNs are operating through this cross correlation technique, this simple cross correlation operation. Here you see an example, so a picture of my dog, a standing watch here. And so a kernel that you might want to set by hand, for example, is the identity kernel. So you only have a one. And so as it parses, it scans the image, it's always just summing the central pixel, so nothing changes. That's the identity kernel. Here you have a kernel that is sensitive to strong derivatives. So it's differentiating the image in the two x and y directions. In both directions, in this case, for x and y. And so applied to this image, what happens is that edges pop out. So whenever there's a strong gradient in the image, it pops out. And so the application of this kernel, this edge detection kernel to this image, that's what you see here. And you can see here, I think you start to get a sense of how those cross correlation operations can be useful. For example, in the initial image, it's very saturated and very hard to distinguish the background. And here, after this edge detection, after the application of this edge detection kernel and cross-correlating it across the image, the background pops out just as much as the rest, even though it was too saturated. That gives you a sense of the kind of operation CNNs are doing repeatedly throughout the network. And so in the two previous examples, the kernel were fixed, set by hand. Here you see a schematic of a classic CNN. So it was designed by Leduc, the same guy again, who develops backpropagation for CNN. So it was developed by him in 1989. And it's really the classic workhorse of CNNs. Even today, this exact architecture is still used a lot. If you have a problem that can be tackled by a CNN, most likely this exact architecture is going to work quite well out of the box. So it's a very famous CNN architecture. In the previous examples I showed you, it was just one kernel fixed by hand applied to the image. A CNN is sort of a regularized, but very generic function that first applies lots of those cross-correlation on the image. So here you have the input image. It's applying kernels, cross-correlating those kernels on the image. And the output image is then downsampled, and the procedure is repeated until there's a list of features, if you will. And at the end of the network, there's a generic nonlinear function. You can think of it, for example, at some generic nondescript function. So for example, a polynomial or something, a high order nonlinear function that makes the decision. And so all this is done similarly to what I just showed you, those kernels post-correlating the image, the input image, but here instead the kernels are learned from the data. And the way they learn, thanks to the backpropagation trick developed by Ian Lequin, is like you would optimize any function. So thanks to the backpropagation trick, those CNNs, those complicated functions are differentiable. And so to optimize those weights, you differentiate the performance of the function as a function of the parameters, all the weights in the network. And that's what you optimize. So you maximize the performance. In practice, you minimize the opposite of the performance, which we call the loss. And you look for a local minimum in this space, high-dimensional space, of the opposite of the performance of the network as a function of its parameters. So that was my brief introduction on CNNs. And now I'll also give a very brief introduction to interferometric synthetic aperture radar, InSAR, because that's what will be the topic of the talk. So the application of CNNs, the development of a CNN to extract information from InSAR data. So here you see a schematic of InSAR adapted from Geoscience Australia. So the basic idea behind InSAR is to take two radar images from the same spot in space, here, and for this case, for satellite InSAR, at two different times. And then computing the interference between those two radar acquisitions. In theory, if there was nothing else in the way, the phase change between those two images is only a function of ground deformation. So that's the basic idea behind InSAR is interferometry from space using radar wavelengths. In practice, of course, the atmosphere in the way. And so to a first order, here I'll show you that it's most of the signal that's gotten from InSAR data is atmospheric signal. So most of the phase change between those two acquisitions I just mentioned to first order is due to changes in the atmosphere in between the two satellite passes. So here you see on the left an interferogram, so the phase change between two acquisitions so actually InSAR data. So phase change between those two dates you see here, two different times in 2004. That's from a paper by Romain Jolivet, he published in 2014. And here you see on the right the predicted effect of changes in the atmosphere on InSAR data. So using a different satellite, properties of the atmosphere are measured, and Romain computes models the predicted effect of the atmosphere on the phase change in the InSAR data. And what you see is that to a first order, they're equal, which means to a first order, InSAR data is just measuring changes in the atmosphere. So before InSAR data can be used, the first step is to remove this first order effect of changes in the atmosphere in between satellite passes. And so in practice, for the rest of the talk, I'll be showing you InSAR interferograms, but that have been corrected from this first order effect of the atmosphere. And so here it's the kind of InSAR acquisitions you see. Here you see them at two different times, so in map view, and color codes the range change. And so this time, after this first order correction of the atmosphere, what remains is really a mix of atmospheric effects that haven't been corrected, so there's remaining atmospheric effects, and actual ground deformation. here I'm showing you those two images because Baptiste Rouet et al. In a paper they published in 2016 found that a slow earthquake took place in those slow earthquake took place and can be seen in InSAR data. So here you see the first interferogram, the first corrected interferogram before the slow earthquake, and here you see corrected interferogram after the slow earthquake. And you might be able to see that there's a sharp offset that runs parallel to this image. And that offset was interpreted by Baptiste Rouet et al. As a slow earthquake that took place on the North Anatolian Fault. And they were able to determine that this offset is a slow earthquake, knowing the North Anatolian Fault is there. So here you see on the upper right a schematic of the tectonic setting. You see here this black rectangle is actually the location of those InSAR acquisitions, those interferograms. And the North Anatolian Fault that accommodates the rotation of the Anatolian plate with respect to the Eurasian plate runs exactly where the offset took place. And that's what enabled Baptiste Rouet to determine that this offset is a slow earthquake on the North Anatolian Fault. And so I've been showing this to show you that even after this first order correction, even after state-of-the-art correction, InSAR time series are still mostly noise, and it takes expertise and a priori knowledge of what could be deforming, in particular of the tectonic setting, to determine what's signal and what's noise. And there is an enormous amount of InSAR data. So InSAR data is collected all over the world every few days. And so there's a real problem in the time it takes to interpret InSAR data versus the amount of InSAR data. And so there's a need for automation. So because InSAR data is so noisy, the standard way to get information out of InSAR data is to either look at very large deformation, such as the co-seismic slip during an earthquake, that would actually dwarf the remaining atmospheric signals after correction, or to look at averages over years and years, which enables the extraction of deformation that has been taking place over a long time. And because those remaining atmospheric signals are more or less random, stacking the data in such a way over years averages out the noise and gets the signal. But to look at transient signals that might be taking place, such as slow earthquakes, and that might be of the order of the noise. So for here, for example, for this slow earthquake on the North Anatolian Fault, there's no technique other than for now looking by eye and determining what's noise and what's signal based on a priori knowledge of the tectonic setting. So there's a need for some automation of signal detection in InSAR data, which is the topic of this project. So the way I've been doing it, the way I've been trying to develop a method to automatically extract signal from those noisy InSAR time series is deep learning, of course. And so for deep learning, I mentioned in the introduction, there are lots of parameters, lots of those kernels that have to be adjusted by differentiating the model with respect to its parameters. And that takes a lot of data. As I mentioned, a breakthrough in deep learning for computer vision applications has been the ImageNet dataset, which has really enabled deep learning to break through. And here we don't actually have a ground truth. We don't have a very large database of InSAR data where signal is labeled and noise is labeled. What we have is a few examples of, for example, earthquakes or of real signal. So where signal is interpreted using a prior knowledge. But even in those cases, for example, in this paper I showed you by Baptiste Rouet et al., they demonstrate that they find a slow earthquake, but it's not like we have a labeled portion of the image that's signal and a portion of the image that's noise. So we don't have ground truth. And so the only way around that is to go the route of synthetic data. And so that's what I've been doing to train those deep learning models, is to train them on synthetic data only, and then apply them on real data, which I'll show you later. So those synthetic data, here for the purpose of trying to find small deformation on faults, consists in surface deformation due to fault, due to slip on a fault. So here in an elastic medium, so it's important to generate lots of data. So it has to be very fast. So it's a somewhat simplistic simulation. So it's using a Okada solution of slip on a fault in the elastic medium, to which are added noise signals that I've been working on with Romain Jolivet and Manon Dalaison, such that it's quite similar to the kind of noise, at least to a first order, that remains after correction in InSAR time series. So there are two main components to those noise signals we add to the slip signal. One is autocorrelated noise in time and space that mimics the kind of turbulences that are in the data. And the second component is atmospheric delays that correlate with ground elevation. And so those are basically due to errors in the first order correction and the effect of the atmosphere. So here you see an example of this kind of time series. So the actual slip that took place in this synthetic time series, you see it here. Why? The ground truth, the label, here we have it. And here the input X is this noisy time series. So the ground deformation, you can sort of see it here behind the noise, on top of which we add these two noise components. And so the time series trained that train the deep learning model are of this kind, and a lot and lots of them. So 10 to the order of 10 to the 7.
Sorry, Bertrand. I'm interrupting with a question. John Bedford. What about topography? Is there any topography in the synthetic model?
Good question. Yeah, thanks. So there is. So as you see, a component of the noise is due to topography. It's correlated to topography. And so this question actually fits really well in my next slide. So it's actually a secondary input to the model. So along with these synthetic time series, to generate the component that's a function of the topography, we also generate a synthetic topography, and this synthetic topography is a secondary input to the model. And so here on this slide, you see actually the architecture of our model. It's a purely convolutional model. So as I mentioned, classic CNNs have convolutional layers followed by so-called dense layers, so a generic nonlinear function. Here, our model is only made of convolutional layers, and here that's the architecture, where time progressively disappears throughout the model, such as at the end there's only information in space of the cumulative deformation that took place during the input time series. So that's the task that our deep learning model is learning to reproduce. So the task is taking an input noisy InSAR time series, so here synthetic, but then later on it will be real time series. So it takes this input noisy InSAR time series, as well as the elevation. It has to output deformation and faults that took place during the time series. And so it sees an enormous amount of examples where it has the input time series and the output actual deformation. And all the weights in the model, which are essentially lots of kernels of the type you saw in the introduction, those weights are adjusted by differentiating the performance of our model in finding cumulative ground deformation as a function of those parameters. And so on synthetic data, this architecture is able to perform extremely well. So here you see results on test data, so data that has not been used to train the model. So it's new simulation, new synthetic data generated at different signal-to-noise ratios. So here you see on the x-axis, and the performance of the model here assessed on those test synthetic data is assessed with R-squared, so it's a coefficient of determination. That's 1 for an absolutely perfect reconstruction, so each pixel would have to match absolutely exactly, and it's open-ended towards minus infinity for really bad models, and 0 is the performance of taking the average of the input as an answer. So basically, it's between 0 and 1, the model is better than just taking the average of the input. So stacking the input. And so here what you see as a performance signal-to-noise ratio. For signal-to-noise ratios around 1, so here you see on the left column of this part of the figure, the last input. So the model takes as input the noisy InSAR time series. Here you see the last element where you have the ground deformation and noise. The second column shows you the ground truth, so the actual deformation due to slip and falls that took place during the time series. And the last column shows you what the model found given this input time series. So for signal-to-noise ratios around 1, it's easy to distinguish the deformation by eye. It's also easy for the deep learning model, no surprise here. But when we reach signal-to-noise ratios around 0.1, it's actually it starts to be the limit of the eye. So here you see, for example, the last output. You can sort of guess this deformation on the fault, and that's the ground truth. So it starts to be hard to do by eye, but it might be possible. And here you see what deformation the model found. So it has absolutely no issue finding deformation at signal-to-noise ratio of 0.1. That starts to be the limit of the eye. It's actually still performing almost as well as signal-to-noise ratios of 1. Interestingly, even for really low signal-to-noise ratios, so a few percent, of which you see an example here, where it's absolutely impossible to distinguish anything by eye, the model still can find some signal. So the default response of the model is interesting also. Its default response is to find no deformation. So when it has a performance on average of 0.2 at signal-to-noise ratios of 2%, here it means that it's finding part of the signal. So even when it's extremely hard or even impossible to find anything by eye. So all this to show you that at least on synthetic data, the model performs extremely well. So this architecture is really optimized. It took quite a while to design it, but it's really optimized to solve this problem of finding cumulative deformation in noisy time series.
Bertrand, sorry, another question. What about if the fault is, imagine the fault is not in the track, and for example, you're in a subduction zone and your track is going along the continental plate.
Right. So for example,
and it's long wavelength. Sorry.
So you mean, for example, if it doesn't reach the surface?
Yeah. So here in these examples, I'm seeing like kind of a signal that is on like a, for example, strike slip fault or a normal fault. But if your fault is to the left of the scene, for example, and you have like a long wavelength deformation pattern, are you still able to pick such deformation patterns up?
Yeah, no, that's a really good question. So it's also trained with deep slip deformation, but indeed, if the wavelength is much larger than the input window, it becomes hard. So as long as the wavelengths of the deformation signals are at least smaller or comparable to the size of the input, has no problem finding the deformation, even if it's deep sleep deformation. But yeah, of course, there's the problem of the wavelength. And a simple way to address it is to simply downscale the data, for example. So that's what we've been doing for this kind of long wavelength deformation. I'll show examples in the next slides. Another route that we haven't taken yet is to increase the size of the synthetic data for then application on real data.
Yeah, thank you.
Thanks.
Bertrand, can I ask another question, please?
Yeah, sure, please.
So the topography question that was asked before, you said it was a secondary input, but
Yes.
I didn't quite catch how that actually worked in the previous line.
Yeah.
So where does that information go in?
Yeah. So in practice, yeah, it's sort of interesting that it's a secondary input that's added basically later in the model. So the noisy time series is a normal input, like you would, so it's basically applying from the start of the CNN. The CNN basically gets rid of time first through pooling, so downscaling on the time dimension, and after it's gotten rid of time, then topography is added as another input. So basically as an additional feature map.
Okay, thank you.
Thanks. So that was it for the training of the model on synthetic data and assessing its performance on synthetic data. An interesting feature of purely convolutional networks is that they learn kernels, so it's local operations, which mean that they're actually invariant with the size of the input. They can be applied to arbitrarily sized inputs. So after training on synthetic time series of a certain size, they can directly be applied on real data of any size, which makes it very, very fast to apply them and out of the box. And so for the rest of the talk, I'll be taking this deep learning model applied only on synthetic data and applying it on real data without any further training. So basically what it will do, it will look for deformation on faults, small deformation on faults in those real data. And an important point is that, again, the only input it takes is the noisy InSAR time series and the topography. It has no other a priori knowledge, for example, on the tectonic setting, etc. And so here you see in the first application on real data, application to the same data where Baptiste Rouet et al. Found a slow earthquake on the North Anatolian Fault. And so as I mentioned earlier, they were able to interpret an offset in the data that you see here again. So here you see the actual time series fed to the neural network with color coding the apparent ground deformation. So you might be able to see this offset that runs along the data. So Baptiste Rouet et al. Interpreted it as a slow earthquake knowing the fault was there. And here in the output of the neural network, I'm plotting the fault. So we can see it, but it's not an input of the model. And so here, this is the output of the model. So the denoised deformation found in this input time series. And if you look at the color scale for the output, it's much smaller than in the input. And so in particular, it finds indeed a slow earthquake here in this section of about 1 centimeter. And that's the section that Baptiste Rouet et al. Identified as sleeping. So that's reassuring. So it's able to find a known slow earthquake noisy InSAR time series, but without a priori knowledge of the tectonic setting. So that's already a big improvement. It can be applied automatically without knowing what could be deforming. And what's also very interesting is that here it also finds that an adjacent segment right after a kink on the fault. That's also interesting. So the sleeping portion seems to be split into by a kink on the fault. And so there's another segment, another portion of the fault to the east of the known segment, of the segment known to be sleeping, that also experience a slow earthquake according to a model, but by a much lower amount, but only a couple millimeters. And so that was missed by Patrice Rouet et al. Because it's simply buried in the noise. So so couple millimeters. If you look here at the input data, we're basically in the signal to noise range of about 10%, where it becomes extremely hard to determine anything by eye. Here we were in the signal to noise range, so 1 centimeter compared to about centimetric noise. So we're in the signal to noise ratio range of about 1, which makes it possible to see something by eye. 10% becomes really hard. Our model finds sleep here in this segment. According to its performance on synthetic data, it's very reliable in this range of signal to noise ratio. So that's the first element that gives us confidence in this signal. A secondary element that gives us a lot of confidence in this additional slow sleeping signal is that the model has no knowledge of the fault. It's not an input of the model. It simply looked at those noisy time series and it's finding the sleep that's exactly on the fault. And the third point that makes us really confident in the fact that that's actual signal is that it's also at the same time as the previously known slow earthquake. So all this to say that here we show that after training strictly on synthetic data, it's able to find sleep on the fault of only a couple millimeters in the line of sight of the satellite, which is about an order of magnitude improvement compared with what can be found by eye. And it does this automatically and without a priori knowledge of the fault. And interestingly, it finds that the slow earthquake, the rupture length of the slow earthquake is almost twice as long as previously known. And also interestingly, those two segments, those two sleeping segments are separated by a kink on the fault. So there seems to be interaction there. Now here I'm showing you the cross-section. So in the previous image, in the output of the neural network, you see those lines across the fault. So I'm showing you in cross-section the output of the model. That's in red. So here you see a cross-section to the west across the segment previously known to be sleeping. The output of our model on this sleeping segment is in red. So you see a sharp offset here that was right on the fault. You saw it previously. And in black, you see the average of the inputs after the slow earthquake and minus the average before the slow earthquake. So the kind of standard processing you do to make the slow earthquake pop out. And indeed, it pops out in black. So that's the input data in black. But as you can see, the amount of sleep is of the same order of magnitude as remaining noise. But still, that shows you that the amount of sleep found by the model is preserved. And so that's an interesting also property of our model. It preserves physical quantities. And here below, on this plot, you see a cross-section towards the east. So across the segment that experienced an about 2 millimeter scale slow earthquake that was missed because it's just too small compared to the noise in the input data. So here you have the input data in black. So average after the slow earthquake minus average before the slow earthquake. And you see that's presumably what's signal when the rest is noise. At least that's what our deep learning model tells us. And also here it preserves the amount of slip. Now we've been looking at data where a known event, a known slow earthquake took place. And since then, we've also been feeding our model years of data about the North Lateran Fault. So I should have mentioned it. The data previously it was from the Cosmos SkyMed satellite. And because our model has been trained on synthetic data, of course, it has no knowledge of the source of the data, so can also apply to different satellites. Here, for the next few slides, I'll be showing you data application of the model to data from the Sentinel-1 satellite constellation. So we've been applying our model to years of data from the Sentinel-1 constellation. Doing so, we find actually a number of earthquakes on this creeping segment of the North Lateran Fault. And I'll be showing you the largest event we found in those data, because it seems to last a while, long enough for us to observe actually the propagation of the earthquake on the fault. And so here you're seeing up top in map view, the line of sight apparent deformation. So again, it's after state-of-the-art correction, those InSAR time series are a mix of actual ground deformation and remaining uncorrected atmospheric signals. So here you see the last input fed to the neural network, a bit like I showed you for the synthetic data in map view. We're looking at more or less the same area. So that's again the North Lateran Fault, the creeping segment of the North Lateran Fault that hopefully you can see here. It's also here. It's probably easier to see here. And below, you see again in map view, the output of the neural network after it's been fed a time series here, of which you see the last element. And pay attention to the difference in magnitude. That's basically an order of magnitude difference. And the output is an order of magnitude smaller here. And so I'll be showing you this movie of the slow earthquake we find and that we can see propagate on the North Lateran Fault. And so as I parse the slides, basically what you see is the deep learning model parsing the time series in increments of 1 and telling us what actual fault deformation took place, at least according to the model, during the input time series. So here we start to see signal, again right on the fault, even though it has no knowledge of the fault. So that gives confidence in the signal. And so here it opened near those red crosses. I'll talk about them later, but it's creep meters. I'll show you right after. So the rupture started near the creep meters and opened, propagated towards the east. The slip seems to intensify and keeps propagating towards the east. More to the east. And the rupture terminates. And so those red crosses are famous creep meters, actually, that have been recording deformation, this creeping segment of the North Lateran Fault for a long while. Here you see them in red, solid and dashed lines. So there's a few creep meters installed in the area. Those two creep meters are only a few meters apart, a few tens of meters apart, 200 meters at most, as I remember. So the cherry creep meter starts here a bit later. So first, if you look at the creep meter, you can see that indeed there's a number of events, deformation event, so slow earthquakes that are apparent on the creep meters and that repeatedly take place on this segment of the North Lateran Fault. What's interesting is that although those creep meters are only a few meters apart, they don't agree that well. So that's interesting. So deformation, slow deformation, those earthquakes the deformation that can be quite local on the fault. So it gives value to being able to observe the overall behavior of those earthquakes on the fault. So here what you see in red is over time, the fault parallel slip, so as measured by those cube meters. And in blue, you see the fault parallel slip that we get from the output of our NOAA network in an area. So the pixels in the InSAR data are quite big compared to the local measurement of those cube meters. So the blue curve is an average of the creep in an area surrounding those cube meters, an area quite bigger than the local measurement of the cube meters. But still, what we see is that we have overall agreement in the total amount of slip on the fault, and we also have quite a good agreement in the timing of the slow earthquake. In particular, the movie of the slow earthquake you just saw was in the summer of 2017. This slow earthquake, it was also captured by the cube meters. So here a figure that's still a work in progress, but I thought I'd still show it because it's quite interesting. So here you see again fault parallel cumulated slip over time. So it's a bit complicated figure, so I'll go through it a bit slowly. So color codes time. So older times are in darker colors, more recent times are in yellow. What you see is the fault parallel cumulated slip. So when you see a jump in the colors, a jump in those lines, it means deformation took place rapidly. Whereas if those lines are bundled together, it means it wasn't deforming at those times. And that's plotted as a function of longitude, so along the North Anatolian fault. And so those plots that you just saw earlier, so those plots of cumulated slip are basically 1 point. So here where there's the black cross, 1 point of those curves. So you can imagine you're actually looking at lots of those kind of step functions. So all those jumps all over the fault are presumably slow earthquakes. So all you see here is as the output of the deep learning model. So because it has no knowledge of the fault, we can be quite confident in the signal it finds. But still, we need to compare it to the cube meters, of course. But the idea is that we have a continuous measure of creep along the fault, and we see a wealth of events of a bit all sizes. So we're still looking at those data. For example, you can see small events. So if those are real, it suggests there might be a scaling, interesting scaling to look at in those data. We see that some portions of the fault are not slipping. That's also interesting. And that's also something we'll be looking at, as well as interaction with the regular seismicity. That's still underway. Now, okay, I'm a bit short on time, so I'll go quickly over the rest. But basically, so this model is developed on synthetic data. It's extremely fast to apply, and so now we can just start playing with it and applying it to all kinds of input time series, which was the point of the project, to be able to find small signals, small transient signals on faults very efficiently. So we start applying it to all kinds of input data, and here we'll be applying it to the Chaman fault, to InSAR data measured acquired over the Chaman fault, Sentinel-1 data again. So here you see the cumulated slip, the cumulated deformation, not the cumulated slip, cumulated deformation in a very long InSAR time series. So from 2014 to 2019, processed by Manon Dalaison and Romain Jolivet and published by Manon Dalaison and Romain Jolivet. So that's a figure from their paper. So you see here in black the Chaman fault, which accommodates the movement of the Indian plate with respect to the Eurasian plate. It's at the border between Afghanistan and Pakistan, Chaman region. And so you see here the kind of standard treatment of InSAR data, which is to look at cumulative deformation over a long duration, so that atmospheric noise, remaining atmospheric noise, gets ridden off. And that's the kind of data that you normally look at. Color codes deformation. So, for example, this blue spot and this one near Keta, for example, is a subsiding area. You might be able to see an offset in color along the fault. In particular, here it gets from yellow to dark red, which indicates the fault is deforming. Here you see also deformation right across the fault near the near the city of Chaman, and those were 2 earthquakes that took place during the time series that I'll be looking at as well. So there's a wealth, all this to say, there's a wealth of signals in those cumulated InSAR data. And so it's cumulative deformation from 2014 to 2019. And instead of doing this standard treatment of InSAR data, just like before, we'll be feeding the input noisy InSAR time series and looking for a transient signal. So using our deep learning model, we get some sense of a temporal variation instead of just having the cumulated final deformation. And so here you see one example of doing that. So I'll take you through those figures. So here at the bottom left, you see the input InSAR data, so the noisy input InSAR data. Hopefully you might be able to see the fault system, the Chaman fault that runs here in the diagonal of the data. So color codes deformation, -3 centimeters to +3 centimeters here in the input data, mostly noise. Again, because we're looking at short time scale InSAR time series. Here at the bottom right, you see the output of our deep learning model applied to the input InSAR data, noisy InSAR data, which tells us presumably the deformation that took place on faults during the input InSAR time series. And here in particular, I fed it the InSAR data that included 2 earthquakes on the Chaman fault, and it does find them. Again, without any a priori knowledge of the fault. So it does find those 2 earthquakes that took place on the Chaman fault this time, so in 2016. And the northern portion of the Chaman fault, so here, up here, where there's a dashed line, is known to be creeping. So if we look at the cumulative deformation, there's an offset and there's no earthquakes, and it's known to be creeping. And here what we find actually is that there are slow earthquakes on this this supposedly creeping segment of the fault. And up here you see the same data. So it's again the surface that shows you the line of sight deformation as a function of longitude and latitude. So really this surface here is the same surface as in this small dash square here. You're simply seeing it in 3D instead of 2D and with a color coding deformation. And here it's the same thing, but in the creeping, but in the input noisy InSAR data. And so in the output, we see quite a strong signal right on the fault on the creeping segment. And the model looks for transient. So it means it found a transient deformation signal in this creeping segment right on the fault. And it wasn't apparent at all in the InSAR data. It's just too small compared to the noise. So presumably the model finds a couple millimeters of slip on the fault, when which gives us a signal to noise ratio of about 0.1, where it's very hard to see anything by eye. But taking the cumulative deformation over years does indeed confirm that this portion of the fault creeps. But actually, it seems that most of the deformation is accommodated by slow earthquakes and not by a continuous creep. So it seems to not be actually stably sliding, like what the cumulative deformation would suggest, but it's actually experiencing repeatedly slow earthquakes. That's what we find from applying a deep learning model on those data. Because the cumulated amount of slip from all those slow earthquakes, so here I'm just showing you one, but we see repeatedly slow earthquakes on this creeping segment, and the cumulated slip of those slow earthquakes explains almost the entirety of the slip on this northern section of the fault. So it's actually mostly experiences slow earthquakes, so still unstable sliding and not stable sliding, not creeping. And so here you see the same output of the deep learning model in map view again, and simply a zoom on it. So if you look again at the scale of the deformation, it's able to find deformation of a couple of millimeters on the fault. And here it's simply a zoom on this creeping segment of the North Anatolian fault. Here you have a zoom of those of a couple of slow earthquakes that took place on this creeping segment. And again, most of the deformation of this segment seems to be accommodated by these kinds of slow earthquakes, of which we see a bunch. And again, the model has no knowledge of the Chaman fault. It simply fed the raw data along with topography, and it doesn't know the fault is there. So if it finds signal right on the fault, it's quite suggestive that it's a real signal. Now I've reached the end of my time, so I won't really talk about it, but I'll just say a few words. But basically, the same architecture can be used to look for cumulative ground deformation other than on faults. So in particular, for example, point sources or underground volume changes, deformation caused by underground volume changes. We can go through the whole procedure of training the model on synthetic data, but this time instead of deformation caused by slip on faults, deformation caused by point sources. It doesn't work as well because interestingly, these kinds of signal are less specific compared to noise. It looks more like noise, so the performance is not as good, but still it works quite well and can at least automatize the process. And here we've applied it also to the Chaman region, when there are known subsidence areas due to aquifer depletion. We find the known areas and we find a bunch of other areas that are subsiding that coincide with the farming in very dry areas. So just all this just to say that the same architecture can be used to look for transient deformation of all kinds. I won't go over this, but it's the same idea. And so I'll conclude. So as I showed in my introduction, InSAR time series are extremely noisy. And the standard way to use InSAR data is to either look at very large deformation, such as a coseismic slip during an earthquake that dwarfs the remaining atmospheric noise, or to look at cumulative deformation over many years, such as the random noise cancels out. To look at transient in InSAR data, that's of the order of the noise, it takes manually an expert interpretation. So I showed you the example of a slow earthquake on the North Anatolian fault. And because of the difficulty of finding signal by eye below the noise level, the limit of the kind of slow earthquake, slow slip events that can be found by eye knowing the fault in noisy InSAR data is about 1 centimeter, and I showed you an example. The deep learning model we developed, it's designed to look for transients, which gives us a time resolution that's directly a function of the repeat time of the InSAR data. But for example, for Sentinel-1 data, in the base cases, it gives us a time resolution of about 1 month. The point of designing the model, it was to have a method that automatically finds deformation, so it's fully automatic. And from results on synthetic test data, as well as from results on the North Anatolian fault, it's able to reach 1 millimeter scale detection. And the application of the model to Sentinel-1 data over the North Anatolian fault enables us to watch a slow earthquake as it unfolds. And so now the idea is we're able to find events that are about an order of magnitude smaller. And so we're expecting to find at least an order of magnitude more events. And so we can do this automatically. And now the goal is going to be notably to gather statistics on those slow earthquakes, and where perhaps we'll be able to see interactions emerge between different modes of slip and faults. And so, yeah, I also showed that it extends to deformation from other sources. And so that was it. Thanks a lot for listening to me. It was a pleasure to give a talk in this seminar series by Chris Marwan, and thanks, Chris Marwan, for inviting me.
No, certainly welcome. Please, everyone, unmute long enough to thank Bertrand for a fabulous talk. Use the raise hand feature. I see Roland Bergman already raised his hand, so Roland, go ahead.
Yeah, thank you for your talk, Bertrand. I have two quick questions. Did you try to estimate how deep the fault creep extends in the various slow slip events on the Northern Anatolian fault? And the second part of the question was, do you see any association of microseismicity, either in space or time, with the slow slip transients?
Thanks for the question. So we started inverting basically for the signals we find, and so we're trying to after we get those clean output signals, now we're inverting for slip, and that's how we try to get that depth. So we started doing that. I don't have slides to show, unfortunately, because it's really work in progress. But yeah, so that's the idea of how we do it. So we don't go the route of asking directly the deep learning model for the source parameters. We prefer to go the route of having the clean signals and then doing a simple inversion, regular